This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. The series parallel analysis from the perspective of the voltage source is now complete, and now we can move on to the next step, which necessitates we perform the same analysis for the remaining current source. This means we need to remove the voltage source by replacing it with a short circuit. Note that when we redraw the as-analyzed circuit, including the short, the nature of the circuit is again fundamentally changed. Current produced by the current source must travel through R3, right to left. Current then splits into two paths, one afforded by R1, the other through R2, and returns to the current source. A Kirchhoff's current law analysis of the as-analyzed circuit suggests that IB equals I3, which equals I1 plus I2. I3 must equal 18 milliamperes traveling right to left. An application of Ohm's law demonstrates that V3 is 3.6 volts, positive to negative, right to left. An application of the DC current divider rule suggests that I1 is 6 milliamperes traveling right to left. An application of Ohm's law demonstrates that V1 is 2.9 volts, positive to negative, right to left. An algebraic rearrangement of the Kirchhoff's current law equation suggests that I2 is the remaining 12 milliamperes traveling top to bottom. Voltage across elements in parallel is the same. R2, being in parallel with R1, also has a voltage drop of 2.9 volts, positive to negative, top to bottom. An application of Ohm's law proves this to be true. V2 is found to be 2.9 volts, positive to negative, top to bottom. Now that we've completed independent analysis of this circuit from the perspective of both sources, the only task remains us is to summate the effects accounted for magnitude, polarity, and direction. Given the voltage source induces a 32 volt drop, positive to negative, left to right across R1, and the current source induces a 2.9 volt drop, positive to negative, right to left across the same resistor, it can be said that when these effects are superimposed upon one another, R1 ultimately experiences a 29.1 volt differential, positive to negative, left to right. The effects of both sources are opposing one another, and it makes sense that the final voltage drop will be less. Similarly, when the voltage source pushes 66.7 milliamperes through R1 left to right, and the current source pushes 6 milliamperes of current through R1 right to left, these sources are opposing each other, and it can be said when these effects are superimposed upon one another, R1 ultimately experiences 60.7 milliamperes of current left to right. Given the voltage source induces a 16 volt drop across R2, positive to negative, top to bottom, and the current source induces a 2.9 volt drop also across R2, positive to negative, top to bottom, it can be said that when these effects are superimposed upon one another, R2 ultimately experiences an 18.9 volt drop, positive to negative, top to bottom. The effects of both sources are aiding one another, and it makes sense that the final voltage drop will be increased. Similarly, when the voltage source pushes 66.7 milliamperes of current through R2, top to bottom, and the current source also pushes 12 milliamperes in the same direction, R2 ultimately experiences 78.7 milliamperes of current traveling top to bottom. Again, the effects of both sources are aiding one another, and it makes sense that the final current will be more. Lastly, R3 experiences a voltage drop in current because of the current source. As a result, R3 finally experiences a voltage drop of 3.6 volts, positive to negative, right to left, and 18 milliamperes of current traveling right to left. If we wanted to, now that we've got final voltage and current values, one could calculate for nonlinear properties like power. Lastly, it should be noted that the final results should make sense, and in no way should they violate fundamental electrical properties like Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. As an example, consider an application of Kirchhoff's current law at the top central node. 60.7 milliamperes of current enters from the left through R1. 18 milliamperes of current enters from the right, traveling through R3. 78.7 milliamperes of current leaves the top central node, traveling through R2, top to bottom. 60.7 plus 18 does in fact equal 78.7. What came in has indeed come out. Ultimately, voltage source A is forcing 60.7 milliamperes of current in a clockwise loop in the following fashion, and current source B is forcing 18 milliamperes of current in a counterclockwise loop in the following fashion. And R2, the shared element in both these loops, experiences both currents in an aiding fashion. It makes sense. Before we bring this lecture to a close, allow me to demonstrate a practical application of the superposition theorem. I will readily admit the previous illustrated example For that matter, most illustrated examples of the superposition theorem you find in your average textbook are impractical foolery, only encountered rarely in the field. A lot of superposition theorem examples are simply meant to put your series parallel circuit analysis skills to the test and serve no practical purpose. Not so this one. Consider a series opposing relationship of two voltage sources and a single current controlling resistor in between. We explored such an application in the DC voltage sources in series circuit lecture, available at the Big Bad Tech channel. This is essentially a primitive battery charger. The 14-volt charger on the left-hand side forces current into the deeply discharged battery, presently at 10 volts, on the right-hand side. The current controlling resistor, presently set at 4 ohms in between, makes sure current is maintained at a manageable level. We really don't need to use superposition theorem to analyze this circuit, given Kirchhoff's voltage law analysis could produce usable results quicker. However, Kirchhoff's voltage law and the superposition theorem should both yield the same results. Let's see if the superposition theorem rises to the challenge. Traveling in a clockwise loop around the circuit, an application of Kirchhoff's voltage law demonstrates the rise of 14 volts is equal to the voltage drop across the resistor plus the 10-volt drop across the deeply discharged battery. An algebraic rearrangement of the Kirchhoff's voltage law equation, solving for the unknown voltage drop across the resistor, demonstrates the resistor experiences a 4-volt differential, positive to negative, left to right. An application of Ohm's law demonstrates 1 amp of current flows out of the 14-volt charger and into the deeply discharged battery, presently at 10 volts. The reversal of current flow in a lead-acid battery will reverse the chemical process that occurred during discharge and will recharge the battery. If we left the battery in this state, we might expect the battery voltage to rise over time. Let's see if the superposition theorem yields the same results. Remove the deeply discharged battery from consideration by replacing it with a short. The charger would force current in the clockwise direction, and the current controlling resistor would experience the full 14-volt differential. An application of Ohm's law demonstrates current will be 3.5 amps traveling clockwise. Let's now do the same analysis from the perspective of the deeply discharged battery. Remove the charger from consideration by replacing it with a short circuit. In this case, the deeply discharged battery would force current to travel in a counterclockwise direction, and the current controlling resistor would experience all 10-volt differential, positive to negative, right to left. An application of Ohm's law demonstrates the deeply discharged battery would cause 2.5 amps of current to flow in the system. Now let's summate the results. 14 volts, positive to negative, left to right, minus 10 volts, positive to negative, right to left, demonstrates the current controlling resistor ultimately experiences 4 volts, positive to negative, left to right. Similarly, 3.5 amps left to right, minus 2.5 amps right to left, demonstrates the current controlling resistor experiences 1 amp traveling left to right. The results obtained using superposition theorem do indeed match the results obtained using Kirchhoff's voltage law. I've got a reasonable degree of confidence these results are correct. If you've got the time and inclination, one could use techniques like mesh analysis, nodal analysis, or circuit simulation software to again confirm these results. The point being, there is one right answer, and regardless of the techniques employed, you should get that one right answer. My affection for the superposition theorem largely stems from this simple fact. If you can perform series parallel circuit analysis, you already know the superposition theorem. You don't need special techniques like mesh or nodal analysis. All you have to do is use series parallel circuit analysis, stay organized, and properly summate the results, accounting for polarity and direction. Alright, this concludes the theoretical portion of this lecture. Is that it? No, your acquaintance with the superposition theorem is just beginning. Really, the only way to understand superposition theorem is by doing superposition theorem. In the spirit, stay tuned because I've got another complete lecture coming your way real soon featuring nothing but applications of superposition theorem. Believe me, you'll get plenty of practice. In conclusion, we learned to employ the superposition theorem in an effort to solve our desired electrical quantities for circuits with more than one source. Special use techniques like mesh and nodal analysis can yield the same results. However, the superposition theorem does so using techniques you should already feel confident in, notably traditional series parallel circuit analysis. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.